Describe the effect of different ligands on the splitting of d orbitals. Well, I'm going to start by drawing out just the electron configuration for copper. To argon, 4s1, 3d10. Remember, that's one of those weird ones. Copper and chromium are the weird ones. Putting in arrows to represent the electrons, following Aufbau, Hund and Pauli rules. Now I need to make it into an ion, because complexes need ions, at least in this part of the syllabus. So I've knocked off the electron from the fourth shell, the valence shell, to make a copper 1+ ion. Water is behaving like ligands. It has a lone pair of electrons capable of making a dative covalent bond with a central transition metal ion or atom, and I've coloured those in purple. Now those ligands, those water molecules, cause the d orbital to split. The ligands cause the metal ion d block orbitals to split. It's a 3-2 split. If I was to shine light through it, actually in this case nothing happens. For a colour to be seen, you need a partially filled d orbital, and this d orbital is completely full. There is no room for an electron to be promoted from the lower to the higher. Well, what does that matter? Well, we'll find out in a second. But a partially filled d orbital is what we need if we're going to have a coloured complex. So what colour is no colour then? Well, colourless, or you could say no colour, or white. Sometimes confusingly black, but we'll stick with no colour or white. Let's reset this little experiment. And there's copper again. I'm going to make it copper 2+, putting off a couple of electrons there. Now I have a partially filled d orbital. And that's going to give me coloured complexes. So I'm going to bring the water ligands in again. Now I could use ammonia, I could use hydroxide, chloride, cyanide. All of these are different ligands that will split the d orbitals in different ways and give different colours. Again, in purple, purplish pink, is the dative covalent bonds. The d orbital split, it's a 3-2 split. And now when I put light through, some of the light's disappeared. So this is going to look blue. I shone all the colours in at the beginning, red, orange, yellow, green, blue, indigo, violet, and only a few colours came out, the bluey colours came out. So this will appear blue. So what happened to that energy? Well, it shakes those electrons around, and one of them may be promoted from the lower to a higher energy level, and that took energy, and that was the energy of that light. So that's what happened to the light. It was removed by the action of putting an electron up to a higher energy level. Now we might ask you what colours. We'll tell you what colours absorbed, and you have to tell us what colour the compound is, or vice versa. So here's the trick. Roy G. Biv, put them in a circle, all the colours. I don't have blue, indigo and violet on my active board, so I put B, I and V. If orange is absorbed, then your compound will appear kind of bluish. It's opposite. If green's absorbed, then my compound will appear kind of violety reddish. So whatever colour's absorbed, look across the colour wheel to see the other colour. It's called the complementary colour, and that's the colour of your complex.